All right, so hello guys, welcome. Thanks for joining our session. Third day on reInvent. I still hope you're doing good. Yeah? All right, nice. So my name is Mike Winkelmann. I'm a senior data scientist at XL2. You've probably not heard of XL2 until today. It's a joint venture of Capgemini and Audi. I'm joined here by an amazing team. Together, we've brought this project to life with a strong focus on innovation and collaboration. Please, guys, go ahead and introduce yourselves.
Yeah, hi, my name is Thomas. I'm IT architect at XL2.
Hi, everyone, or as we say in Germany, Bavaria, Servus zusammen. My name is Edward. I work at Audi as the project lead and the enabler for AI solutions in the planning department of Audi.
And hi everyone, also from my side, I'm Simon. I'm an external PhD student at Audi, and I'm researching about the use of generative AI for the factory planning domain.
So thanks guys. We are really excited to be here at reInvent and talk about how we have used Gen AI to streamline Audi's tender process. Before we dive into the details, I would like to give a quick outline on what to expect in this session. We will start with a very basic introduction on LLMs, what they are and how they work. After that, Audi will share their vision on how to use LLMs in their tender process. We will then highlight the customer-centric development approach we chose for making sure that the product we developed met real-world needs. After that, we will give a quick overview on the high-level solution design. And right after that, we will dive into the architectural deep dives for all of you guys who like the tech stuff. Next, we will share what currently is in development and also what the future holds for our product. Then it's getting pretty exciting, where we will share where we stand today through a system demo. And finally, we will wrap things up by giving you some key takeaways to take to your own projects. All right, let's start with an introduction to LLMs. As I said, it's a very basic introduction, so we are doing quite a lot of simplifications here and there. But I think nevertheless it is quite useful to get a better understanding on the topic of LLMs. So let's start on the left-hand side with some key facts about LLMs. So LLM stands for Large Language Model. And large can be taken pretty seriously. So GPT-4, I think most of you have used it through ChatGPT, is estimated to have about 1.8 trillion parameters. So that's huge, and explains why they are so expensive to train and even expensive to run. They are a language model. That means they're capable of understanding and generating very human-like text. An LLM is also most of the time a so-called GPT. And GPT stands for Generative Pre-trained Transformer. Generative, again, just means that the model is capable of generating new content, like drafting some text for you, answering in a conversation. I think you all have experienced that by now. They are pre-trained on huge amounts of data. So basically, you can say they're trained on internet scale amount of data. And by training on so much data, really some interesting capabilities emerge in those models, which you are probably also aware of because you've used such models. Transformer refers to the deep learning architecture used for those models. That architecture was introduced back in 2018 by some very smart guys from Google through the paper Attention is All You Need, and that was really a tipping point in the NLP area. I think what makes the transformer architecture so successful is that it allows you to do this training in a very parallel fashion, and that allows training on such huge amounts of data in the first place. So now let's switch to the right-hand side and look how such a model works, how it is generating text. So basically, what an LLM does is it gets a set of ordered input tokens and generates a probability distribution of all possible output tokens. So that might still sound complicated, but if we now make the assumption that one token is an English word, it basically boils down to you give it a piece of text and it predicts the most likely next word. But how is it doing that? So first, the model needs a vocabulary. And the vocab basically is the set of tokens known to the model. So in our example, basically that means all English words in existence. Each of those tokens, or in our case words, has a learned vector representation in very high dimensional space, which is called an embedding. And those embeddings are aligned in that high dimensional space so that they encode some kind of semantical meaning of those tokens. And what that then happens during inference is that those vector representations get adapted from the model by two important things. So first, the vector representation gets adapted by position information, and secondly, that's probably much more important, by context information, by attending to every other token in the input. And adapting the representation basically means it moves in this high dimensional space. And by doing that, the last token in the input set encodes all information the model needs to predict what the next most likely token is. So in our example, in winter the sky is often, the model says with 80% certainty, gray. Yeah, to be honest, when I made that example, I was in Germany, so now being here in Las Vegas, I probably should have written in German winter, yeah. But I think still you get the point there. What is also important to say here is you can slightly adapt those models by using the information encoded in those embeddings to do other things. For example, you could use the maybe average embedding over all tokens in the input to encode the semantic meaning of a whole sentence, right? And by doing so, you could do some kind of similarity search along text. I mentioned that because later on that will be important, so that you've heard that before. Yeah, so that's basically a very simple introduction to LLMs. I hope it helped a little bit in understanding things.
Great, thanks, Mike. So let's get a little bit into the subject matter here. My department at Audi is responsible for the planning and construction, the next generation of our engine production. And for this production of these very complex products, we need special machinery. So at a very early stage in the product development process, we need to write down all the requirements of those special machines to procure those machines. And at Audi, we call this specification process the tender process. Basically, the tender process can be divided into two core steps. First one being the description of all the requirements of the machine. And the second one is the matching of possible potential offers to our tender and making a final statement. So the planner describes all his requirements in this tender document, which can be quite complex. Those requirements come from various sources like the product development, the research team, or the technology development who wants to implement the newest manufacturing technology in the next generation of assembly lines. So it's not surprising that those tender documents can have more than 400 pages fully stacked with technical informations. Even for our best experts, it's kind of hard to keep track of every information within these tender documents. And just to give you an overview, we're talking only about the planning department of Audi here. We have far more than 1,000 tenders per year. And the problem becomes even bigger if the potential suppliers respond to our tenders here. We get multiple offers per tender. We're talking here about 5 offers up to the number of 50 offers per tender. And trust me in that matching those offers to our tender is very labor intensive. To prove that, let's do a little calculation here. For simplicity, let's say we have 1,000 tenders per year, though we know it's usually much more than that. And per tender, we get an average 20 offers. So that sums up to 20,000 offers per year at Audi planning department. And just to quote a colleague of mine, we need 1 week of labor to do a final statement per offer. So that sums up to 20,000 weeks engineering, well-paid engineering weeks per year. So we have around about 800,000 engineering hours for reading, replying, and comparing two documents to each other. There's a huge potential here, and we are not even taking into account that our research team or the development guys, or even the whole Volkswagen group, not only Audi, uses a very similar tendering process. We can do that better. What if we can use LLM that can understand and generate human-like language to help us to compare this tender to an offer? And after 1 year in this project, we can say, yes, AI can help us with that, and we will show you how we reach that goal.
Okay, so let me start with a question. I guess you all heard about chat with your data as an approach, and I'm asking in which organization you don't have any chat with your data like initiative going on at the moment. Yeah, there are no hands, which I also expected, because even though this was the spark that started this whole project, we were very aware when we started it that, two things are going to happen. First, this technology is very generic, and it will very quickly become a commodity because it's so easy, adaptable to all kinds of domains. And this actually happened by the end of 2023. A lot of vendors had it already incorporated into their offers, and it was not really something to stand out. And the second thing is that we realized very quickly, the planners, they don't need something to just chat with the documents, to just ask questions to the documents. So we had to go on and find something of real value for the planners. And the real value of this technology that we found out was that we can compare pieces of information together. We can compare something, a requirement from a tender, with all the chunks of data that come in a single offer. And we need to build something based on that and make something that brings much more value to the planners' day-to-day work. So we started the research, and we talked to some planners, and we quickly found out there's no standard way of doing things. Everybody developed their own way of, like, some people just put comments to a vendor's PDF directly, or some people really print out a whole offer document, put it to a wall, go with a text marker over it to piece together the relevant information. It was a real analog process, and everybody developed their own solution to this process, to the problem that they have to deal with such vast amount of information on both sides, the tender side and the offer side. And our idea was to make this information manageable in some way. And we need to build a system which does that, reducing the overhead of dealing with so much information. So we started some research. And what we found out, what a lot of planners did was at the very beginning, they start to list the requirements that come with a tender in an Excel sheet. They just put like 100 to 200 rows of requirements, and then they go cell by cell for each offer, fill out the document to get a summary of all the offers that come in. And this was the starting point for us. Okay, here is something that we can maybe provide in a much more automated way for them. And this is also where we put the lever for our system. So, okay, we already gained this information very early. So we started to talk with the planners more. And one funny anecdote was At the very beginning, the first planner that we talked with, he started the whole conversation with the sentence, so you are the people who are building the system that will replace us. And we all laughed a little bit about it, but yeah, we knew at the very core, there's a real problem we had to deal with. That is the fear of the people that we built the system for, that it will take their job at some point. And it's a very real fear. So we had to mitigate that fear in a way that they would understand, okay, no, we're building a tool for you. You're not something that will replace your expertise, because this expertise, it comes with years and years of dealing with vendors and getting a lot of experience how you need to deal with vendors and how to deal with technical details of the whole process. What we could do was reducing the work that nobody liked to do, matching information together. And the easiest way how we could achieve this was to build a POC from the very beginning, a very low-tech POC, which had no server-side components at all. It was just one tender, one offer. And what it did was you could click on one side and would just scroll and highlight the relevant information in the other document. You could just click on one side and in one document and it would scroll on the other side to the right place. And this was something that the planners, they could really grasp from the very beginning. They could see the value in it because they could see themselves using that tool. And this was like a good tipping point for us, because when we showed it to them, they were really on fire for the tool, and they really wanted to help us and wanted to be integrated in the whole process of like building this tool step by step. And this is what we did. We did several iterations with the planners to get to a point where it really matches their process and it advances their user experience.
Yeah, so until now you got a good overview about the use case and our project setup. Now I would like to start and talk a little bit about how we built our solution for the tender process. So how did we bring AI into the tender process at Audi? So as you might already got, this is a really time-consuming and also complex process. So we needed to break it down into smaller steps which are more manageable for us. And the first step here is to make our documents LLM ready. So, like in almost every AI-related project, we need to prepare our data first. So, what does it mean, data? We have several formats of documents. So, there are Word files, PDF files, even PowerPoints or Excel are used for the tenders or the offers. And we have also different modalities into these documents. So there were information inside of text, we had tables, and also figures and drawings, which were very important for us that we can get the information out of these elements in order to have a good evaluation at the end. Furthermore, we also needed to understand the structure of the document. So my colleague said these documents are really long, often more than 400 pages. We need to break down these into more smaller and more manageable blocks, which we do by extracting the structure of the document. When this is done, we go to the second step. Here, we have at first a look only at the tender file, and we extract relevant requirements out of these files. Here, we create a checklist, which we can use later on for the evaluation. And here it's important for us that we know where from the document we extracted the points in the checklist that we can later on match these requirements. Another point which is important at this step is that we include our domain expert. So, as we said before, we're not going to build a tool that replaces the planners, but to support them. And here, we need input from them so that they can also feed their own experiences and preferences into the tool, so that they will benefit most in the end from our evaluation. When this is done, we come to the third step, and finally, the offer comes into place. In the third step, we want to match the requirements we extracted from our tender file with relevant part in the offer. So we at Audi try to force our suppliers to answer our tenders in a specific structure, that this step is done pretty fast. But most of them don't follow our instructions. And I guess for those of you who are also dealing with tenders might have similar experiences. So what we need to do here is that we look through the whole offer where we find relevant parts which meet our requirements, even when they are distributed over the document. And another point, the challenge here is our domain-specific language. So we have most often German documents, which contains a lot of domain-specific keywords. Both of these things are not the best when it comes to AI models. In the last step, finally, evaluation takes place. Here, we check how well the offer meets our requirements. And the challenge here is that we don't have a binary classification by results. So we cannot say this is good and this is bad. So we have some fuzzy results categories and also some results which are in between the approval or not approval. So there are things like we need further clarification, even internally at our company or in discussion with our supplier. So for these classifications, we also need to include the expertise for our domain expert.
All right, so, thank you, Simon, for sharing the general solution approach. Now we'll follow a deep dive into the architecture. Basically, you will recognize a lot of things Simon just mentioned, but with a little bit more technical depth. Before doing so, I would like to quickly highlight our journey from the pre-Bedrock area into the Bedrock area, because when we started that project over a year ago, Bedrock wasn't generally available. So we started by hosting open source models on SageMaker using text generation inference containers from Hugging Face. And please don't get me wrong here, I love open source, I think it's super important. I'm also a contributor myself, but we really faced some issues here. So at that time, open source models often lacked good documentation. So setting them up correctly was kind of tricky because you often didn't really know, okay, what's the correct prompt template to use? What is the correct setting for the text generation inference container to apply? So it really was not hassle-free. Also, managing the scalability of the endpoints really was not trivial because we were in a POC phase, so we faced a lot of big on-demand quota and then basically scaling down to zero. I mean, it was doable, but it was, yeah, like I said, a little bit of a hassle. When Bedrock became available, it basically gave us a very elegant solution to all of those problems. So first, it gave us easy access not only to open source models, but also to closed source models like Anthropic. It also gives us, and I think that is really one of the greatest features of Bedrock, a unified converse API. So you can really easy and quickly change to different models within your application. And honestly, Bedrock just works, right? It's super easy to use. It scales at least to our demands pretty well, and it's reliable. So switching to Bedrock really helped us to shift our focus from managing infrastructure to solving business problems. But now finally, let's have a deeper look into the architecture, starting with the document preprocessing pipeline. So like Simon mentioned, the assets we get for the tenders and offers, they have multiple different modalities, from PDF documents to PowerPoints and Excels. So the first step, and all steps, as you can see, are succeeding AWS batch jobs orchestrated by a step function. The first step is really about extracting the text out of those different document assets. And we chose on using an OCR service for doing that, AWS Textract. And using an OCR service for that really gave us some key advantages. The first one being that you basically can read text out of every asset that is convertible into an image, and that is basically everything because it's OCR. So by choosing OCR, we didn't really have a problem with all those different document modalities. The second key advantage is that the AWS TextRec service does not only provide you the extracted raw text, it also provides you the document layout information, and that is a huge enabler for different things. First, it allows us to really increase the data quality from the text we extract. To give a simple example, maybe in the original document there is a table that crosses multiple page borders. We can just merge them in post. So we have one beautiful table in raw text. And there are more things, but I think that's a good example. The second advantage of having the layout information is it's a cool enabler for some things in the front end, which we will later see, like, for instance, auto-scrolling, because we have the position information from the text we extract. The third key advantage, and that is probably the most important one, is we can use the layout information to chunk our document in a way that the chunks are as coherent as possible. The LLM cannot really work on the whole document, so we have to provide it little chunks, and having coherent chunks really makes the whole process much better. And we basically use title and section header informations to create those chunks. And that really increased the quality of our product. So having extracted the raw text, the second step is about extracting information encoded in images. Like Simon mentioned, oftentimes there is important information in images. Again, that step is basically enabled by having the layout information, because we know where in the documents there is an image. So we can extract the image, then feed the image with the surrounding context to a multimodal LLM. In that case, you see we use Claude 3.5 Sonnet, and generate descriptions for those images. So we also include the image information in raw text. The third step then is about chunking and embedding. So chunking, pretty straightforward. I just explained we can use the layout information to create the chunks out of the document. And then we create embeddings out of those text, which we will later on use during retrieval for semantic similarity search. So basically, when we then start from a requirement, we use semantic similarity to retrieve matching parts out of the offer documents. So RAC, basically. For the embedding model, we chose Titan V2 from Amazon. I think it's a pretty good model by balancing performance and cost. It is also capable of handling multiple different languages. Simon mentioned for us German is pretty important. It handles German pretty well. And it is also capable of handling quite large contexts, because our chunks still tend to be quite long. So the last step then is an optional one. I mean, it's not done for offers, but for tenders, basically, we now iterate over the chunks we extracted. We give those chunks to the LLM and ask the LLM to pre-structure by giving us or extracting for us a list of requirements, by giving us a title and a good description on what the requirement is about. So by doing so, we also have a unified base for comparing to different offers, which is also important. And yeah, I mean, we have to persist the data we generate, and of course, we go for a Postgres on Aurora. Since we have some vector data, Aurora can also handle that. Just use the PG vector extension. So there was no need for us to go for a specialized vector database. So we have covered document preprocessing. Now let's switch to how online inference works and how it incorporates the SME, the subject matter expert, to ensure that we have a reliable and robust process. So the first step is, I think it got mentioned multiple times, is about involving the SME and letting him cross-check the extracted requirements out of the document. So basically, we give the SME the option to either add a requirement that was missed by the LLM, or delete a requirement that is not really relevant, or maybe slightly adapt the extracted requirements. If the SME is then happy with the extracted list of requirements, he can start the inference process by just a click or two in the front end. And what then happens is, basically what I mentioned before. We do retrieval by semantic similarity search. For a given requirement, we search in the different offer documents for matching chunks for that given requirement. When we have retrieved the information, we give the requirement and the retrieved information from the offer documents again to the LLM. And we ask the LLM to answer if that requirement is met by a certain offer. And if it is met, we also ask the model to give us citations in its reasoning. This is pretty important since it helps the SME later on to quickly check if he follows the reasoning or not. So that's basically exactly what the last step is about. It's again about involving the SME and letting him check the results of the SME and maybe adapt them if necessary. So this whole online inference process is enabled by some AWS key services. We use AWS AppSync for the GraphQL layer, connecting the client to the backend. We use Lambda for managing the inference logic. Again, Bedrock for talking to the LLM and for using the embedding model. And of course, again, we use the Aurora database for managing the data and managing the search. So by combining automated inference with SME oversight, we really found a good balance of using AI-powered speed, but ensuring that we incorporate SME's expertise, which is key for Audi's tender process.
Okay, so before we go to the demo of the front end, I want to tell a little bit about the current developments we are facing. So what we build right now is all built with the vanilla models. Like we use vanilla Titan embeddings, we use vanilla Sonnet LLM, and we thought, would it make sense to fine-tune something? Would it make sense to fine-tune an example in LLM to our domain expertise? And in these thoughts, we quickly came to the conclusion that the biggest improvement that we could see is probably in the retrieval process, which means we could generate better embeddings that are better fitted to our domain. Because I will describe this real quick. When you have a look at the right at this schematic graphic, it shows for a single query, when you have one requirement and you go over all the text chunks from a single offer, it's actually hard for the model to really distinguish between relevant and irrelevant part. This is due to the fact that these vanilla models, they are trained on like world knowledge. They are not specialized on any domain or anything, so a huge part of this whole space that an embedding can fill is taken for all things totally irrelevant to our process. So the idea is here to get a better separation, because here when you look at this graphic, it can mean that for a retrieval, some totally irrelevant parts get a better similarity score than parts that might be key parts that you need to do a real inference on it. So the idea is here to train the model on really domain expertise. And how do you get that domain expertise? You need to ask the subject matter experts, which are the planners in our case. And we need them to manually match requirements to the parts of the offers that they see as most relevant. And when we have built this like golden sample, as we call it, we can then go on and build a synthetic data set out of that. And that synthetic data set then has the quantity that is needed to do an actual fine-tuning step on some open model. And we are currently in the process of building this golden sample to go through that process. And actually, fine-tuning a model itself, it's pretty cheap compared to how much it costs to train like a foundation model. You can go in the millions or billions of dollars for training a foundation model, but fine-tuning a model can be done for some hundreds of dollars. And the real challenge here is to build a data set that's really representative for you. And we are in that process right now, even though for us it works good with what we have, but here we can really make a jump forward in our opinion. So now I will hand over to Simon.
Questions we will of course do in the end, so no worries.
Yeah, I think now is the moment you all waited for. Now we'll have a look into our demo and see how we included all these functionalities into our front end. So here you can see our web application. Basically, there are 3 columns. On the left side, there is our structure we've extracted from the tender document. So here, the user can navigate through the document and see in which part of the document he's currently working. On the right-hand side, we have the possibility to see our tender file. So this is the first step where we create this checklist. On the right-hand side, we go through the tender, we have PDF viewer functionalities, and see how in the document the things are written. Here in the middle of the screen, actually the action happens. So here we can see the checklist which was created from our LLM. And here the domain expert also can include his domain knowledge. So it's possible to remove points in the checklist, to add things to the checkpoints, or even add completely new checkpoints. And all of these things were directly used for the evaluation later on. So as you can see here on the screen, they include some new checkpoint, and we can click on this plus button, which edits it directly to our checklist. So once this is finished and the domain expert thinks, okay, now let's evaluate this chapter, he can click on the button below, where he starts the comparison process. It's important to mention here that when we start this process, we can do this chapter by chapter, so we don't have to wait until every colleague has finished the evaluation of his specific chapters. So now, this takes a little bit. Let's jump to another chapter which was already evaluated. And here, you can see now in the middle the generated results from our pipeline. At this moment, I quickly want to stop our demonstration to see why we profit from using similarity search. So the first point in this checklist here is something about 3D layout planning, which was a requirement we set. When we look into the offer, which is now displayed on the right side, we see that in this chapter here, it's mentioned that a software called SolidWorks, which is actually used for 3D layout planning, will be used to do this. But in this step of, or in this chapter of our offer, it's not mentioned anything about 3D layout planning. But with using the semantic search, our system is able to capture this and use this specific part of the offer for the evaluation of our checkpoint about 3D layout planning. So let's continue with our demo. From the layout, you can again see that we have 3 blocks. On the left side, there is again the structure. On the right side, now, as I mentioned, there we can see the offer. It's also possible to pop out several parts of this window and to use it on a second screen, which was one of the requirements given by the domain expert. Here, I already gave a little introduction what's happening here in the middle. So here you can see these points, which I marked now. So 5 means the LLM thinks that this specific part from our checklist is met by the offer on a level out of 5 out of 10. So all of the checkpoints are evaluated by the LLM, and now our subject matter, again, can do his own evaluation provided with the basis from the LLM. So here, he can go through the process checkpoint by checkpoint, and for each checkpoint, he can say if a point is approved, not approved, or needs further clarification. It's also possible to jump in the offer to the relevant parts, which we matched in the step before. So this also helps the planner to speed up his process if he needs to look something up in the offer from the supplier. We also have the possibilities to switch your view and see how the original tender file was used. Or even here, we see that we can see the whole checkpoint which we created before, that if we want to have this information again on the screen. I guess now we will come to the point where we can switch the view, and here we can see now our tender file again. So this is maybe the way the planner worked before. He has two documents side by side, and he can also have this possibility to use our tool and see what he has written in the tender file and what the supplier wrote in the offer. So when all of this is done and every chapter is evaluated, or even in the middle, we can also download the information to have it in an, for example, Excel file to use it for further evaluation. This is how we do it. This is our tool for the AI tender process, and this is already used by our planners, and they like it.
Okay, thank you, Simon, for showing off Audi's TenderToucan. I'd like to conclude with our key takeaways for you. The first one being pretty obvious, carefully planned cost. We all know Gen AI is not cheap. Try to find a matching model and a matching performance to make business here. The second one, and probably the most important for us, we need to understand the SME, in our case, the technical planner, because their needs and their process is what we have to translate in our Gen AI solution. And the last one, even though, of course, the responsibility is still for the SME, for our technical planner, we created a balance between the human and the AI interactions, and therefore created a co-working atmosphere here between the AI and the human, and benefit from the synergies here. And now I'm giving the word to Mike for the last slide.
Yeah, I think, yeah, thank you guys for attending our session. There's a lot of things we have in our minds to improve the project. So if you have any questions or would like to discuss with us your ideas you have, please feel free to come forward and visit us. Yeah, and again, thank you really much for attending this session.